Now let's take a look how we can describe uniform circular motion. We've been using the x and y coordinates, for example, of a particle as it moves in 2 dimensions, and we can still do that if we talk about something moving along a circle. But if something is actually following a circular path, there are other ways we can describe its motion. So what we're going to do is we're going to use angles to describe where the particle is. So that means, for example, if we wanted to describe where the particle is, we could use what's called the angular position. And so here's the idea. We have a dotted line here. That's our reference line that we're going to use to measure from. It would be like x equals 0 along a line if you were moving. That's going to be our 0 angle reference. And if we draw a solid line from the center of the circle to the actual location of the particle, then we can define an angle theta here, which describes where the particle actually is. As the particle continues to move, that angle will change. Now, we want to think about how to define that angle in terms of radians. We have the blue line here, that's called the arc length. That's the actual distance traveled along the circular path by the particle, starting at our reference location. And r there represents the radius of the circle. Then by definition of a radian, the angle is just s over r. It's the arc length divided by the radius. So radians are a very natural unit for measuring angular positions because they represent a ratio of 2 very meaningful distances. The arc length, the actual distance traveled along the circle, divided by the radius of the circle itself. So that'll describe where the particle is as it moves around in a circle. We can also talk about how fast it's moving. Now, of course, we can always talk about the velocity, how fast it's moving along its path, but if we're going to be describing its location with an angle, we can talk about how quickly that angle is changing as the particle moves around the circle. And so that's known as the angular velocity. It'd be in radians per second. And so, just like we take a time derivative of the ordinary position to get the ordinary velocity, we can take a time derivative of the angular position to get the angular velocity. So we would take d theta dt, and so if we take the time derivative of theta, assuming the radius doesn't change, we're traveling along a consistent circle, we just get ds dt, which is literally your speed, v, and then divided by the radius. So omega, and that funny symbol there is a lowercase Greek letter omega. That's the standard symbol for angular velocity. That's just going to be v over r. Now, if we want to write down the position in x and y values, we could do it like this. In terms of the angle theta and in terms of the radius, we could find the x and y coordinates of our particle. So the x coordinate would be r cosine of theta, which is omega t. If you're moving with a constant speed around that circle, that means omega, your angular velocity, will be a constant. And so at any given time, you take omega times t, that'll tell you the value of the angle, assuming you started at theta equals 0 at t equals 0. So in any case, we have r cosine of the angle, angle's omega t, that's the x coordinate, and we have r times the sine of the angle, times omega, sine of omega t, to get the y coordinate. So if we carry out our normal derivative, just taking dr dt to get the actual velocity of the particle, what we get is this. So we take the derivative of the x position. So remember, r is a constant, so we just take r times the derivative of cosine omega t, and that's going to give us sine omega t, negative sine omega t. And then when we use the chain rule, that also pulls out a factor of omega. And omega times r is v. So for the x component of the velocity, we have minus v sine omega t. And then when we take the derivative of the y position, again, r is a constant, so we just take the derivative of sine omega t, that's going to be cosine omega t times omega. And when we group omega and r together, that's a v again. So we get v cosine omega t. So if you actually plot a few values of that velocity, you will see, in fact, that that vector is always tangent to the circle and points in the direction that the particle is going. So I'll leave that as an exercise for you to try. Maybe one simple example, if you put in t equals 0, then for the x component of the velocity, we get sine of 0 is 0, so we have 0 for the x component. For the y component, we would just get a positive v. So that's a vector pointing straight up with a magnitude v, and that's exactly what the velocity would be right at t equals 0. Now, if we want to find the acceleration of the particle, then we would just take the time derivative of the velocity, dv dt. And so again, that means we take a derivative of each component separately. And here's what we get in that case. You take the x component, we take, again, v as a constant, so we take the derivative of sine omega t, that's going to be cosine omega t times omega. So that means we get a minus v omega cosine omega t. And if you substitute in what omega is, v over r, you get minus v squared over r cosine omega t. We do the same thing for the y component, and that changes the cosine back to a sine. We get another factor of omega, and so we get minus v squared over r sine omega t. So that's going to be the x and y components of the acceleration. So this is just taking simple derivatives of sines and cosines. Now, if we were to plot those out, you will discover that that vector, that acceleration vector, always points toward the center. In fact, if you compare the acceleration vector back to the position vector, you'll see the only difference is the magnitude, r as opposed to minus v squared over r. That's a magnitude. But the components, x component has a cosine, the y component has a sine, but there's a minus in each of the components with the acceleration. In other words, a position vector pointing from the center to the particle is one thing. The acceleration will point exactly the opposite direction. It's going to be toward the center. It's a centripetal acceleration. Now, if we find the magnitude of the acceleration, we would use a Pythagorean theorem on those two components, and you just get v squared over r. So if you like, this is where the formula v squared over r actually comes from. Now, if we go back to what we've learned about velocity and acceleration in two dimensions, we had the velocity and the acceleration. We found components parallel and perpendicular to the velocity. And we said the parallel component had to do with changes of speed. We can be even more explicit now about that component. In fact, the parallel component of the acceleration is dv dt. It has to do with how rapidly the speed itself is changing. And now we can also be a lot more particular about the perpendicular component. We know it has to do with changes of direction, but we now know that that's equal to v squared over r. So if we can find the acceleration, break it up into components, we now have an exact interpretation for the two components. The parallel component tells us dv dt, how quickly the speed is changing, and the perpendicular component is equal to v squared over r. That tells us how rapidly the object is actually turning.